I want to do a practice problem with the Lagrangian mechanics, and I want to stay with one variable, but I want to do something fun. So imagine that I have three different wires, and a bead can slide along those wires, and we want to see which one's going to get to the bottom of the wire first. And this is kind of the origin of Lagrangian mechanics, because the problem was, what path would a bead follow in the shortest amount of time? And solving that problem kind of led to the Euler-Lagrange equation, which led to Lagrangian mechanics. Okay, so how do you find a path that minimizes an integral? That was what that was. And so it turns out that we can model motion in Lagrangian mechanics by calculating the Lagrangian, which is just the kinetic energy minus the potential, and then the differential equation comes from the Euler-Lagrange equation, which is the partial derivatives with q, where that's one of my variables. Okay, so I have three paths. So here are the three paths that I have. I have just a straight line. I'm going to do that one first. I have a circle. I'm going to do that one second. And then I have a parabola. And they all started in at the same point. And I don't really know which one's going to be the fastest. I would imagine the circle, but we're going to do it. We're going to find out. It's not about that, right? The real shortest path is a cycloid, which is kind of difficult to model, to calculate, and I don't want to do that. So I really just want to practice doing Lagrangian mechanics. Let's just get to it. Okay, so I'm going to start with this one right here. So I'm going to redraw that. It's kind of small. So how many degrees of freedom, how many variables do I need to fully describe that situation? And this is going to be the point negative 1, 1. So that they're all going to start from the same point. Well, there's a couple ways I could do this. I only need one variable. Yes, you could use x and y to determine where that position is, but they're linked, right? So I don't need both of them. In this case, what I want to do is to declare this variable right here, the distance up the track as s, and I'm going to call the angle of the incline alpha, which you don't really have to do, but we're going to do it that way. So suppose that is my variable, s. Well, what I need to do is to get the Lagrangian in terms of s. And it's not always trivial to do that, but we can do that. So think about in Cartesian coordinates, my kinetic energy term is 1/2 m x dot squared plus y dot squared. And remember that x dot is dx dt. That's just a notation that we use. Okay. So if I know that, I know the velocity in Cartesian coordinates. I also know, in this case, the potential energy, the gravitational potential energy is mgy. I know that in Cartesian coordinates. So if I can get a connection between s and the Cartesian coordinates, then I can find my values. So here, let's call this x and this y. Well, it's pretty easy to see that x is going to be equal to s with negative s cosine alpha, right? Because that's just this component of that triangle. And whatever alpha is doesn't really matter. And then I can find y is just going to be s sine alpha. Now I can use these to find my derivatives and plug them in there. So x dot, if I take the derivatives with respect to time, s is a variable, so it's going to be negative s dot. I have to take the derivative of that. And then I have cosine alpha. And then I have to take the derivative of cosine alpha, but that's just a constant, so that's it. And then the same thing for y dot. Y dot is going to be s dot sine alpha. Now I can square that. X dot squared is s dot cosine alpha squared. Y dot squared is s dot sine alpha squared. So my kinetic energy term is going to be 1/2 m, and then I get s dot squared. Let's just factor that out because you can see where this is going. S dot squared times cosine squared alpha plus sine squared alpha. And cosine squared plus sine squared is 1, so I just get 1/2 m s dot squared. And you could say, duh, right? Because it's just moving in one direction. I could call that the x direction. The velocity is definitely just that 1/2 m, that direction derivative squared, that velocity squared. Yes, I know. But we're learning here, right? This is not just about getting the answer. And then for my potential, that's pretty easy. It's just mg S sine alpha. Okay, so let's write down my Lagrangian. I'm going to erase this. So I have L is 1/2 m s dot squared minus the potentials minus m g s sine alpha. Okay, so now I can take that and I can plug it in up here and I can find my derivatives. Let's just start with this one, the partial of L with respect to S. So that's a partial derivative. All we care about is S. So S dot doesn't count. I don't care about that. I only care about this one. So if I take the derivative of this term, I get 0. The derivative of this term is going to be negative mg sine alpha. Negative mg sine alpha. That was easy. Okay, now the next term, I'm just going to do the partial of L with respect to S dot. The partial of L with respect to S dot. Okay, again, all I cared about is S dots. There's only one term there. I use the power rule, so I get 2 times 1/2 is 1 ms dot. Now I need to take the derivative, the absolute derivative of that with respect to time. And so I get ms double dot. Now if I put that all together, I have negative mg sine alpha minus ms double dot equals 0. Now what I want to do is to solve for s double dot. So s double dot, the masses cancel, is negative g sine alpha. So that's my differential equation. That's where Lagrangian mechanics gets us. It gets us that differential equation. Now I want to model that. And this one you could solve, right? You could integrate this twice and get a solution, but I'm not going to do that. Instead, what I'm going to do is I'm going to break this into short time intervals. You know that's what's going to happen. So I can say s double dot is going to be delta s dot delta t, where delta t is maybe like 0.01 seconds, and that's going to be s2 dot minus s1 dot over delta t. Now I can solve, so s2 dot is the velocity at the end of the time interval, s1 dot is the velocity at the beginning of the time interval. So if I solve this, I get s for s2 dot s1 dot plus s double dot delta t. So I can find the velocity at the end of that time interval. I can do the same thing with position, and I get s2, s1 plus s dot delta t. So I can model the motion of that even though I don't have to. I can do that. Now, I do need one thing, alpha. I mean, you could get that in a couple different ways. Obviously, it's pi over 4, right? If this is at 0, 0, and that's at negative 1, 1, there's a 45-degree angle. Right. I didn't think for a second. It's a 45-degree angle. Okay, so let's just plot this and make it move along the path, and then we'll come back and we'll do the next one, which is a circle. So I'm going to switch over to Python because I do want to animate this, and then we can learn a lot about animation and stuff too. So let's make a graph. They're all going to be in the same graph. G1 equals, I'm using WebVPython. If you haven't seen this before, I don't know where you've been, and that's fine. So should I give it a title? No. X title equals X. Y title equals Y. I'm going to plot X versus Y. I'm going to plot a trajectory. So I want like equal sides. So I'm going to give it a width. Again, I got to spell things right. Equals 400. Height equals 400. And then I do want to like make it not scale, so I can do that. Let's just say X min is equal to negative 1.1. Y max is equal to 1.1. I think that should work. And then we'll call this F1 G curve color equals color dot blue. And that's all just setting up the graph. I do need G. G is 9.8. And I need my angle alpha. Let's just do it the full way. Alpha equals pi over 4. That's what I said. I need my initial S. I need my initial S velocity, S dot, and I need my time. So in this case, S is at the point negative 1, 1. That's my X and Y value. So that's actually going to be equal to the square root of 2, right? So you go over 1, up 1. So the distance is square root of 2. S dot is my velocity is 0. T equals 0. dt equals 0.01. And now let's say, I'm going to do this for a time loop first because I always mess up with negative signs. So while the time is less than 1, and then we can change that. rate 100. So rate 100 says don't do more than 100 loops per second, and then it will plot that in real time. Oh, up here, dot equals true. So that's going to leave a dot on the front of that. It's going to look cool. Okay, so down here I'm going to calculate S double dot. SDD dot is what I call that, and it's negative G times sine. I forgot for a second. Times sine of alpha. Now I can use that to update S dot. S dot equals S dot plus S double dot times dt, and then I can update S. S equals S plus S dot times dt, and I'm going to plot it. F1 dot. Oh, I need time to. Let's plot it. Okay, let's calculate x. I'll call this x1 and x2. x1 is going to be equal to negative s times, looking at my equation, which I already erased, it's negative s cosine alpha. And again, you don't have to do this way. I'm trying to do it in a very formal way to be formal. S times s sine alpha. And then I can plot that. So x1, this is y1. x1, y1, and then I need to update time. T equals t plus dt, and it just runs for 1 second. Let's just see what happens. Okay, so I didn't put the max. I should have done that. I mean, I guess I could do that because all the graphs are going to be the same. But it looks good. We can print out the velocity if you want. I think it's fine. Well, I'm going to print out the velocity just to make sure. So let's make up here x max is 0.1, y min equals negative 0.1. And then down here, I want to print out the final velocity because that's something I know what it should be. This is print s dot. I don't even care about labeling it. Because if I use work energy, I can find that final velocity, even though it didn't get to the bottom. So let's actually do this while s is greater than 0, less than 0, greater than 0. S is a positive number. See, that's why I did time, because I'm going to make that mistake and it'll go on forever, but I think this will work. Okay. Okay, and so there's my velocity. Everything's good. It works. Great. Okay, let's go on to the next curve, which is the circle. So I'm just going to erase this so we can really get into everything that we need. This one's not too hard. And I'm going to parameterize the curve in a different way just so we can get some different stuff here. So I'm starting right there, and there's my curve. Okay, so again, I need one variable to determine where this is. And so in this case, let's just say that this has a radius of r, and this is the angle theta. So I can determine where that is. So again, the next thing I need to do is to say, well, what's my x value? My x value is just going to be this r times sine theta, negative. Right, because it's in the negative x direction. And then y is going to be this distance right here. So this distance is this distance, right? And that's r cosine theta. So this distance is r, so this is going to be equal to r times 1 minus cosine theta. And hopefully you've seen that before. I don't want to spend a lot of time on that. So my kinetic energy term, I'm going to take my derivatives. X dot is going to be r is constant, times the derivative of sine theta, which is cosine theta. But then I use the product rule, the chain rule, and take the derivative of the inside. So the derivative of theta is theta dot. And y dot is going to be equal to, so in this case I have, this is equal to r minus r cosine theta. So the derivative of r is 0, so I just get the derivative of cosine theta, which is minus sine, but I have a minus here, so I get r sine theta, and again, theta dot. So now I can do my potential energy, my kinetic energy terms. Let's just do it. So T is 1/2 m x dot squared, so it's going to be this. I can factor out the r squared theta dot squared, because they both have r squared theta dot squared, and then I get, surprise, cosine squared theta plus sine squared theta, and that's just 1. And then my potential energy term is mgy, and here's my y. No, that's my y. So that's my y. Let's write it like that. So this is going to be mgr minus mgr cosine theta. So my Lagrangian is 1/2 m r squared theta dot squared minus this stuff. So it's going to be minus mgr plus mgr cosine theta. So now I can start taking derivatives. Let's do the partial of L with respect to theta. Partial of L with respect to theta. This does look like a pendulum. It is a pendulum, and you'll see why. But it's useful to work it out. Okay. The partial of L with respect to theta. No theta, right there. That's my only theta. So I'm going to get the derivative of cosine is negative sine. So I get negative mgr sine theta. Now let's do the partial of L with respect to theta dot. So here's my only theta dot. So I get m r squared theta dot, right? Because I bring the power rule down. And now I take the derivative of both sides with respect to time. So there's only one thing that depends on time, and it's that theta. So I get theta double dot. I hope I didn't skip too many steps with that, but it's not. It shouldn't be too bad. And now I'm going to take this minus that. So I get minus mgr sine theta equal minus mr squared theta double dot equals 0. So theta double dot, if I divide by m r, I get negative g over r sine theta. And that is, in my previous video, that's identical to a pendulum motion. Right? This doesn't know that it's not at the origin. It doesn't know. It's just a mass on a bead that just doesn't know. Okay, let's go ahead and model this one too in our Python. So again, we're going to do the same thing. Calculate theta double dot, update theta dot, update theta, and then transfer that to x and y so we can plot it. Are you guys having fun? Okay. So I need another graph. Let's say f2 equals g curve, color equals color dot red, dot equals true. I need some other variables down here. I need theta. Theta is going to start as pi over 2. Theta dot is 0. I think that's it. I need r. Let's just put it in here. R equals 1. Okay. So down here, I'm going to do it all in order. Theta double dot is negative g times sine of theta. That's why I used alpha before. Divide by r. And then I'm going to update theta dot. Theta dot equals theta dot plus theta double dot times dt. And then I'm going to update theta. I'm going to put it all in order. Theta equals theta plus theta dot times dt. And now I need to convert my theta. Using my theta, I need to find x2 and y2. I already have those equations, right? x2 is, I got to look, negative r times sine theta. Negative r times sine of theta. Y2 is going to be equal to r minus r, let's do it like this, r times 1 minus cosine theta. And that's that. Now I just need to plot it. Now I'm going to have an issue here, but that's fine. F2 dot plot x2, y2. But let's just run it. I didn't even save this thing. Should I save it? Let's save it. 3 curve. I'll change that title later. I am going to give you the link to the code because you know I'm a code sharer. Okay, so let's run this. Nice. 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 Okay. Now we have to do the one that's a little bit more complicated. Not too complicated, but more involved. Let's say more involved. So now I'm going to erase this. I can keep that. I'm going to erase all this other stuff. A parabola. It's kind of hard. It's kind of hard to draw. I mean, I want it to not be a circle. So I know the equation of this graph up here is going to be equal to y is x squared. If I know my x value, I know my y value. So how to parameterize this? Yes, I could use the distance along the curve, but that's not something that you just know. That's not an easy thing to convert between x's and y's. So in this case, I could actually just describe the location of the bead with the value x. If I know the value of x, I know the value of y. So I know everything. And I could have done that for the other ones too, but I want to be different. Okay, so that means that x is x and y is y. I already have it. Let's go ahead and write down the kinetic. Oh, I should take the derivatives. X dot equals x dot. Duh. Y dot is going to be, I have to take the derivative of this with respect to time, so it's going to be 2x. Oh, wait, it's an actual derivative. It's not just a partial derivative, so I need to take the derivative of x with respect to time, and I get x dot. That was a mistake that I would always make as a youngling. So let's write the kinetic energy, 1/2 m x dot squared plus this, which is going to be 4x squared x dot squared. So I could write that as 1/2 m x dot squared. I don't even know if I should. 1 plus 4x squared. And now for the potential energy, I get mgy, but y is just x squared. So my Lagrangian, L, is going to be equal to, I'm going to run out of room. Let's put it up here. L is 1/2 m. I kind of feel like I'm just going to make these all separate terms, because otherwise I'm going to make a mistake. So I'm going to multiply this out. L is 1/2 m x dot squared plus, now I have 1/2 m times 4, so it's going to be plus 2 m x squared x dot squared minus the potential, which is mgy. So it's going to be minus mg x squared. Okay, now let's do our derivatives. The partial of L with respect to x is going to be, I'm just scanning along looking for x's. No x. Here's an x. So because the derivative of that's 0 with respect to x. So here I get 4mx x dot squared. Right? I'm not going to take the derivative of x dot because it's a partial derivative. And then over here I get minus 2mgx. Now I'm going to take the partial of L with respect to x dot. And I get, right here, I get mx dot. Right? The 2 comes down, and that's fine. And then here I get 4mx squared x dot. Now you see that it's not just x double dot for the derivative here. Let's just write it out. D dt, the partial of L with respect to x dot. Okay, so this term is easy, mx double dot. Now this term, I have a product rule. So let's do the x first. I get 2 times 4, so plus 8 mx. And then I have to take the derivative of that, so I get x dot. And then I had another x dot right there. And then I need to take the derivative of that, so I get plus 4mx squared x double dot. That looks wrong. I feel wrong. I feel wrong right now because this is 8mx x dot squared. I get an x double dot term. I should get some terms to combine here. Up here, I'm going to x dot squared. OK, that's going to combine with that. OK, let's just do it. So it's going to be this minus that. So I get 4mx x dot squared minus 2mgx minus all of this stuff. So I get minus mx double dot plus minus, see, minus 8 m x dot squared minus 4 m x squared x double dot. Okay, and that's equal to 0. Okay, I want x double dot, right? Because once I have x double dot, I can update x dot. So I don't have to solve the whole thing. So let's just, that's x dot. I'm just looking for the x double dot. I have two of them right here. I have an x double dot and I have an x double dot. So let's move those to the other side, and I get m times x double dot plus 4 x squared. Wait, I factored out that. Okay, so let's just factor out the m. So I get m times x double dot plus 4 x squared x double dot. And then I'm left with this stuff, 4m x dot squared minus 2mg x. That one, that one, that one. Is that right? Okay, I think I'm right. Okay, so the mass cancels. And now I can, that's an x double dot. I can factor this out. X double dot times 1 plus 4x squared. I can divide both sides, and I get x double dot is going to be equal to 4x x dot squared minus 2gx over 1 plus 4x squared. Whoa. Okay, that's what I got before. Okay, I did check that one because you can make, especially when you're working on a board, you can make some mistakes. So I already have my relationship between x and y. I should be good to go. Let's just go ahead and jump to this one. Okay, we have one more curve. What color should we make it? Green? Red, green, and blue makes sense. I've never been impressed with the green color in WebVPython, but I'm going to make it green because that's what you want. Color equals color dot green dot equals true. Okay, so I'm going to need some new variables here. All I need is x2 and y2, right? So I'm going to say x3. x3 is going to be -1. That's what I'm going to start it with. I don't actually need the y. Okay. So I do need the x3 dot. x3 dot equals 0. Yep. Okay. Let's just leave this same loop the way it is. Down here, I calculate s double dot, theta double dot. I need to do x double dot. So it's going to be x3 double dot, and we're in x3. So I'm just going to type in that equation. So I get 4, I can't even see it, 4 times x double dot, x dot squared. So 4 times x3 dot squared, that's that term, minus 2gx, minus 2 times g times x3, divided by 1 plus 4x squared, 1 plus 4 times x3 squared. Okay, that should work. And now I'm going to update x3 dot right down here. x3 dot equals x3 dot plus x3 double dot times dt. And then I'm going to update x3. x3 equals x3 plus x3 dot times dt. And then I need to calculate y3. So let's just do that right here. y3 is going to be x3 squared. Now I'm going to plot it. f3 dot plot x3 y3. I'm kind of scared about this one, but you know, it is what it is. Yeah, it went the wrong way. Look at that. What did I do wrong? x3. I think I called x3, I called x positive in my equation. And so I need to just make this minus. Let's just plot minus. The y will take care of itself because it's squared. No. That didn't work. Okay, x3. Let's just, what if I just print x3? So x3 is x3 dot. So x3 starts at -1. So that's not that. X3 dot plus x3 double. Maybe I got x3 double dot wrong. Maybe there's a minus sign there. That's a bad idea. Oh, that worked. Okay. Okay, so which one got there first? Let's run that again. Let's run it in slow motion. So change that to 50. So this, oh, the parabola one got there first. I'm kind of curious, just to double check, because I feel like I could have. It looks like a parabola though, so I think I'm going to be okay. But I don't want to check, because if I'm wrong, I'll be mad, and I've already have a 30-minute video. And you definitely get the idea. And if you made it this far, you get the idea. Okay. And if you could, what I would do as a homework, this is a homework assignment. Check the final velocities. They all should have the same final velocity because energy is conserved in all three cases. Okay, now we can start to do more complicated Lagrangian problems, problems with more than one variable or more interesting things, and we will do that. That's the end. I'll talk to you guys later.